Good evening, Knoxville. So tonight I'm going to share with you just a brief little snippet of a few of the projects that are going on at the College of Architecture and Design in a partnership that we have created with Skidmore Owings and Merrill, one of the foremost architecture firms in the world, Oak Ridge National Laboratories, and our own Institute for Smart Structures. The projects that we're going to talk about today are more or less focused around this idea of additive manufacturing. And the first one we're going to talk about is AMIE. So meet AMIE, Additive Manufacturing, Integrated Energy. Additive manufacturing being 3D printing, integrated energy being a net zero building. So we were sort of pushed in this direction by Oak Ridge. They said, we've developed this technology, but we don't know how it applies to architecture. What can we do? Well, we have wonderful graduate students. So we set them to the task of figuring out what are the opportunities and constraints afforded by this new material, a new material that architects have never worked with. So they looked at natural precedent and, oddly enough, origami. Natural precedent makes sense because nature builds with a process of accretion and deposition. That's exactly what additive manufacturing is. So they proposed, wouldn't it be great to make a little visitor center that we could take around the country? We could show people how integrated energy and additive manufacturing works. So this particular project was looking at seashells, how the curve is actually the structure, how translucency, opacity, all of those things are built directly into the exterior fiber of the structure. In addition, we were looking at paper folding. The fact that if you take something extremely thin, like an additively manufactured exterior envelope, it can be only a half of an inch thick, but depending on how that's bent or folded, it can be extremely strong. So these are the things that the students did. They passed that information on to Skidmore Owings and Merrill, who took over the professional aspect of developing the first prototype, which is here. So what you see at the top of that image is a C, one of the kind of, I would say, the base module of AMIE. Two C's joined together to make a ring. The rings are joined together to make the shell. And those rings are held together under tension by 4 tension cables. It's a very small structure. It's entirely mobile. It produces its own energy, and it can share it with an automobile. So in plan, it's just one room, and you can see by that zigzag exterior wall, the wall is incredibly thin, and those walls are self-shading windows. So if the window is facing south, there is no direct sunlight ever hitting that glass, which reduces the energy needed for the building to keep it cool. So when you look at the blow-up, you'll see that that exterior wall is incredibly thin. That's 1/2 of an inch thick of carbon fiber reinforced ABS. That is the entire structural capacity of that shell. In addition to that, there's a little bit of insulation. It's vacuum insulation. So 1 inch will give you an R value better than the wall of your house at home. So this is a new technology. It's cutting edge, but we have to demonstrate it because there is no manual that we can refer to determine how to build with these things. Here's the rendering of the interior. What's interesting about this method, it's direct from digital. That rendering was created from a digital model. That same digital model is the one we send to the manufacturing center at Oak Ridge to print AMIE. So if we get it wrong, they get it wrong. We can't blame a contractor. There's no one in between. So it's a fascinating new world for designers. That's a snippet of the 5,000 lines of code that it takes to make 1C. X, Y, and Z coordinates. That's the print head. So that's depositing those ribbons, those little 1/4 inch thick ribbons of carbon fiber reinforced ABS. This machine tamps them down, readies the next one, it builds up in the Z direction. The bed that it's built on is 20 feet long, 8 feet wide, and 6 feet tall. So that gave us the size of one of the C's. 2 C's go together and make a ring. This ring is about 400 pounds of material. It took about 7 hours to print. That printer is the largest in the world, but there are others now. But at the time, this was the largest architectural scale print ever made. So after we've printed those modules, we join them together, and then we can assemble them here on the chassis. This was done at Clayton Homes facility here in Knoxville, another fantastic manufacturing partner. And you can see here we've coated the exterior with a white coating. That's to cut down on heat gain in the space, but also to protect that carbon fiber ABS from UV. Don't worry too much about the fact that it's ABS. That's changing. Very soon we'll be able to print with entirely bio-based material. Here's the interior. Looks a lot like that rendering, right? Thank goodness. Notice the color of the floor. It's clear who made this, right? We were able to also integrate things like LED lighting in the floor and the ceiling. We can build that directly into the print. And it's here to kind of demonstrate a potential for a future architecture. Here's looking in the other direction. It's the same space. You just turn 180 degrees and the view completely opens up. That vehicle in the back left is the paired hybrid automobile. This building and this car can share power through an integrated link. If the building needs more power, it can take it from the car. If the car needs more power, it can ship it to the car. So This building has garnered a lot of attention. It's been in the media. I think we've had 3 scholarly reviewed papers developed from this. It's won several architecture awards, and I think it's traveled through 4 or 5 states. But this was just the beginning. So then we went back to the architecture studio, remember those graduate students, and we said, okay, we did this, what can you do with it? So they said, what if we could renovate a building and we could 3D print all the components? We could build in the wiring, we could build in the plumbing, we could build in the HVAC, and if someone moved out or those components no longer worked, we could grind them up, print them again. It's a net zero life cycle. It's the same material again and again. Pretty fascinating. Or, as opposed to the rings in AMIE, we could extend those rings into rooms, and we could build a room at a time. And depending on how we configured those rooms, it would be fantastic for things like a natural disaster relief housing, or maybe military applications. And unlike AMIE, which has to kind of stand by itself, what if we could stack these vertically? What if that module had structural integrity such that we could have 5 tall? We could absolutely do that. What if we could change the interior to fit a different need? And again, when that need changes, there's no need to throw that in a landfill. We can regrind that material and use it again. So we've been playing in this field now for a little bit of time. Local Motors, another local great company, came to us and said, you know, we just have the first commercial version of this BAM, Big Area Additive Manufacturing device. What can you do with it? So we tasked undergraduates this time and said, design us a structural system based on bone structure, the trabecula of the human bone. That's what they created. These undergrads were able to prototype this and build it in 1 semester. So I'm happy to say here in East Tennessee, we're developing a fantastic worldwide expertise in additive manufacturing of polymer, and we're creating a fantastic team of people to push this into the future. So thank you for your time.